Hi, my name is Susanna Sharayan, and today we'll be going to Lawrence Hall of Science and exploring a lot of different interesting exhibits and explaining the physics behind it. So stay tuned.
Our first exhibit is a model of our solar system. This is a representation of planets orbiting around the sun. This little coin represents our planet, and now when we're gonna put this coin into this thing, we can see how it orbits around the sun in this funnel. Let's try.
Okay, so let's break this down. Imagine that a coin is a planet like Earth that's orbiting around something. For example, in our case, it's sun. And the closer it's spinning to the center, the faster it has to go. For example, how Mercury is spinning faster than, for example, Pluto. Because Mercury is like the closest to the sun, it has to spin faster. And the reason for that is the force that keeps something in the orbit is centripetal force, and it comes from gravity. That force is balanced by object's inertia, its tendency to move in a straight line. And so the closer to the center, the gravity is stronger, and the object has to move faster to maintain its balance and not to spiral in. This exhibit is a great representation of our solar system, but it's incomplete, and this is one of the key differences why. So first of all, coins falls into the center eventually, and in real life, planets don't. Biggest reason why is because there is no friction to slow down the planets in real life, but there is friction on the surface of the funnel that slows down the coin. And over time, this friction steals energy from the coin, causing the orbit to shrink until it spirals into the center. In space, planets keep moving in orbits for billion years, and there is almost no friction to slow it down. So they stay in motion due to inertia. That's Newton's first law that says the principle is that the objects keep moving in straight line unless there is a force.
And that's where the centripetal force comes in.
that.
It pulls the coin
But
towards the
also, in
center of its
orbit,
orbit and
the
keeps the coin moving in a curved
path
orbit.
of the
In the
planets
well,
is
gravity and
currently-
normal
is
force
constantly
combine
changing.
to
It's like
create the
curved,
centripetal
it's not a
force.
straight line. So what's the cause? Why?
Look, I have two balls. What's gonna happen if I just drop them? They fall. Now we can look at our exhibit number 2. Let's go. So this is a machine that blows out air from those two tubes, and they're gonna apply force on these balls. And let's see what's gonna happen if we just try to put them on. If we drop them on those tubes, what's gonna happen? Look at that! It's not falling. I wonder why. How about this one? Oh, it's also not falling. It's even flying higher up. How come?
Okay, let's take a look on this second exhibit. How come when the first time I just dropped the ball, it just fell down? It fell down because of the force of the gravity. There is nothing else to it. You just drop it and force of gravity pulls it down. MG. But in the second case, we drop it just above of the tube, but it doesn't fall down. That's because these machines are pushing air up through those black tubes, and it stays suspended in the mid-air even if it wobbles a little, because the fast-moving stream of air pushing up against gravity. The science behind it is really simple. When air pushes upward and hits the ball, it creates an applied force of air. And that force balances out the force of gravity, which is always pulling the force down. So the force applied using the air is greater than or equal to the force of gravity. And as long as the upward air is strong enough, the ball just floats. But what's the reasoning behind why the ball doesn't just fall to the side? And the fun twist is that that's because of Bernoulli's principle. It kicks in. The principle says that the fast-moving air has lower pressure and the slower moving air has like higher pressure. So the higher the velocity, the lower the pressure. Around the curved surfaces of the ball, the air is moving really quickly, especially on the sides.
This is an image and a great representation of Bernoulli's principle, how it looks like. And additionally, if the ball starts to drift to left or right, air speeds up on one side more than the other. That side ends up with lower pressure and the ball gets gently nudged back towards the center. It's like the ball is trapped in an invisible tunnel of air. And as long as the air flow stays steady, the ball stays centered and like stable. I also forgot to mention that one of the balls goes up higher because it's lighter and because the air doesn't have to work as hard to go against gravity. So that's the reason, because it's lighter.
This is our exhibit number 3. Let's just try going around and see what it does. Are different. I wonder why. As you can see, the tubes are different, but everything else is the same. And here's a great explanation why the sounds are different, even though I'm doing the exact same movement throughout all of the tubes.
Yay! Exhibit number trust. Let's go. Okay, basically, plug, vibration, physics, sound, wavelengths. Yes, let's go. Basically, this next exhibit is a big music, just giant music instrument. That's a representation of that, and it converts the sound waves into something that we can hear. Each of these black tubes is a resonator, and it means that when you plug it or hit it, in our case you plug it, they vibrate. That vibration moves air, and moving air reaches our ears as sound. So how come how come the sounds are different if like you just plug them, right? Should it be the same? No, it shouldn't, and it's not. Because you probably noticed that all the tubes are different lengths. Some of them are longer, some of them are shorter, and they're not they're different heights. So when you plug them, they produce different notes. That's because the length of the tube determines the pitch of the sound. Longer tubes vibrate more slowly, and therefore it creates lower pitch sounds. Shorter tubes vibrate faster, and therefore it creates higher pitch sounds. And that's because how air moves inside of the tube. Longer tubes have more air to vibrate, so the waves take more time to bounce back and forth inside the tube. That's a longer wavelengths and lower frequency, but the shorter tubes have less air to vibrate, so the wave takes less time to bounce back and forth inside the tubes, and therefore it's shorter wavelengths and higher frequency. Higher frequency, higher pitch, lower frequency, lower pitch. That's why when I was walking, I was going from C to G or something like that, and therefore the tubes were getting shorter and the sound was getting higher. The frequency was going up. Yeah. Yes. Okay, now let's talk about how energy is connected to all of this. When you pull back the thing on top of the, basically you get it, and you let it go, you're transforming kinetic energy, energy of motion, into the tube. And the energy from the strike causes the tube to vibrate. And that vibration gets passed into the air, which creates sound waves. So this exhibit is also a great way to understand energy transfer. Basically, this last exhibit combines everything. Music, I know Mr. Roddick loves it, mechanics, and sound waves, physics. Great connection, right? Give me an A, please. Thank you. Bye.